Now we're into chapter B, which is going to be a trig review. We're going to be taking the slope, finding the slope for many trig functions, so we want to review basically what is trigonometry. Now, the basis of trigonometry lies in the right triangle and the unit circle, which we'll see in a second. Now, the right triangle means that one of the angles is 90 degrees. And here, when we have a 90-degree angle, we also like to have what we call radians, and this is pi over 2 radians. And I'll talk a little bit more about radians as we go. So you can just think of 180 degrees as pi radians, and that would be radians as sort of a thing to remember. So let's say this angle here is alpha, and this is point A, point B, and point C. That defines a triangle. Now the definition of the sine, where we write abbreviation SIN, the sine of the angle, is to take the opposite side, the opposite over the hypotenuse. Now the hypotenuse in a right triangle is the side that's opposite the 90-degree angle. That's this one. This is the hypotenuse. And let's say this is length A. I like to pick A because the Greek letter alpha is first letter of the Greek alphabet, and A is the first letter of the Latin alphabet. So it's opposite. And here, you could call this B, opposite. You can actually label that beta, but I'm not going to at this point. Just think of B here as being the base of the triangle, and you can think of A as being the altitude of the triangle. So the opposite over the hypotenuse would be here if I call the hypotenuse H for the first letter, then this would be A over H. And then the definition of the cosine, which we abbreviate as COS, alpha, that's equal to the adjacent side over the hypotenuse. It's the other side. We have the opposite side and then the adjacent side. I like to find the opposite side first, and then the other one's the adjacent side. Hypotenuse, and that would be B over H. So these are basic definitions. Now, I mentioned the unit circle is very important in trigonometry, and that is a circle that has a radius of 1. So this would be 1 for the radius, and then if you do that and make a right triangle in here, then if you look at this angle, which I'll call theta, this is y and this is x, the y-axis. I'll emphasize that's the x-axis, and this is the y-axis. And this is also called then the unit circle. Very important in trigonometry to have a circle with length 1. Then our definition of opposite over the hypotenuse, which is 1, that would be this side here. That is the sine of theta. And the adjacent one is this one down here, which is the cosine of theta. Now this point here, just to emphasize, would be 1 unit along the x and no height, 0. Down here, you would be at 0x and a -1. Here you would be at -1 on the x and 0 on the y. And up here, you would be 0 on the x and you'd be 1 on the y. The radius going straight up, see, that would be 1. This is 1, this is 1, this is 1. looking at here, this distance here, the radius. And this distance here is 1, this is 1, they're all 1, see, like that. Now we can see by Pythagorean's theorem that when you square the side, you square each side at it, you get the hypotenuse squared, which in this case would be cosine squared theta plus the sine squared of theta is equal to 1 squared, which is 1. And this is one of the most important relationships in trigonometry. We call that an identity, an equation like that. So let's look at this idea of radians. If you have a circle like this, and say that the circle has a radius of r, then the circumference to go all the way around is 2 pi r. In fact, you can think of that as a definition of pi. Now, since r, if you double it, you get the diameter, some folks like to write the circumference as pi times the diameter and say, well, the definition of pi is to take the circumference and divide by a diameter. And that's correct. That's very, very good. Or you could just say that the d is 2r and have the equivalent relationship with simply saying pi is c over 2r. Either way works. If we now go to the text, I've given you the big 6. So the tangent is the sine divided by the cosine. And what makes that interesting for us, even more interesting, is that is the rise over the run. So the tangent gives you the slope. That's the slope. That's nice. That's the tangent. And then the secant is the flip of the cosine. You simply flip the cosine, and the cosecant, you flip the sine, and the cotangent, you flip the tangent. So these are the basic ones. Now, a lot of people get confused, and so did I when I looked at this before, and I get confused. I would say here that shouldn't like secant and sine go together? No. Here you got to be careful. And to remember the correct thing here is I want you to remember that when you sign a contract with somebody else, in other words, you co-sign, all right, like this, cosine, then what this is saying is when you you have to have 2 people sign. So I want you to remember this. Who is the second cosine? You have to have 2 people sign the document. And that means secant goes with the cosine, a second cosine. So that's one way to think of it, or brute force memory, or when you use it often, you start to remember, maybe you get done this chapter, it'll be more second nature. Just remember that the secant goes with the cosine when you flip it, and then the cosecant goes with the sine when you flip. Here's a cute little demonstration to show that the angles of a triangle are 180 when you add them up. By definition, a straight line is 180 degrees, by definition. And if you look at here, this z, I like to think of this as z, or L-zova, then the alternate interior angles are the same. So the blue ones are the same. And then here, looking at the z in reverse, the red ones are the same. And then the yellow one is what you're left with. So when you add the blue, the red, and the yellow together, you're going to get a 180. That's kind of cool to remember that. Now back to radians. If we look at the circumference where the radius is equal to 1, then the circumference is equal to 2 pi for the unit circle. That means if you go all the way around, you get 2 pi, right? Because the circle has 1 for the radius, so that's 2 pi. So what they do is say, well, let's call 2 pi an angle. you go around 2 pi. You go around, we usually say 360 degrees. But let's say we have another kind of unit, which is equal to radians. Now, technically, radians here would not really be a unit, because if you look at pi, for example, you take c divided by d and you get pi. That is dimensionless. There are no units. So if we were to look at, say, a piece of pi where we have theta here, and look at this angle, then that angle theta, see, divided by 360 would be equal to the angle in radians, or let's say if it would be, say, arc length s, so we have s there, that would be proportional to s over 2 pi r. But if you looked at this angle compared to 2 pi, going all the way around, that would be the same ratio as taking s, the arc length here, s, and going all the way around 2 pi r. And you could look at this angle as equal to s divided by r, because the 2 pi's would cancel off. Now, if you look at that, if s goes all the way around, it's 2 pi r. Well, if it goes all the way around, then the theta will be 2 pi, because 2 pi r divided by r is 2 pi. So this is the definition of radians, but technically, since I have written it as a ratio of centimeters over centimeters, the centimeters cancel, so really it has no dimensions. But we like to pretend it's a dimension because you don't get into trouble. It's less confusing. So I like to consider it as a dimension. And then if I ever want to convert from, say, an angle like 45 degrees to radians, I would say write this as 45 degrees. And then I multiply by 1, I don't change anything, but then I put degrees down here, and I put radians. And to make this an equal equation, I need to have a pi here, and I need to have a 180 there. Because remember that the rule that we said up back in here is that 180 degrees is equal to pi radians. So when we do this, then we get 45 over 180 pi, and that's equal to pi over 4, which makes sense because if pi is 180 degrees, pi radians, then pi over 2 would get you 90 degrees. And you see why it's helpful to put the radians in there, because it makes it less confusing. Because you say pi over 2 equals 90 degrees, what's that? But you say pi over 2 radians equals 90 degrees. Oh, yeah, I see what you mean. And then if you divide the 90 in half to get 45 degrees, like we have here, then you're going to get pi over 4 radians. Just divide this by 2, you get pi over 4. Okay, once when we have that, we now go to our favorite triangles from algebra. And one of the favorite triangles is to have a 45 degrees and a 45 degrees and 90. Remember, each triangle has a total of 180. So if this here is 90 and this is 45 plus 45 is 90, you get 180. So these are the same size in terms of length. So Pythagorean theorem says 1 squared plus 1 squared, take the square root, gets you the hypotenuse. Pythagorean theorem, square one side, square the other, add them together, get 2, take the square root. So that means here that we can write down the cosine of 45 degrees. Remember, the cosine is the adjacent which is 1 over the hypotenuse. So it's 1 over square root of 2. A lot of high school math teachers would like to multiply top and bottom by the square root of 2 so that you would get the square root of 2 over 2. But when I was in graduate school, professors asked me, what's really wrong with this? Why not just write 1 over square root of 2? So that's a personal preference. And the sine of 45 degrees is equal to the same, square root of 2 over 2. The opposite side is also 1. So you might see this written as the cosine of pi over 4 equal to square root of 2 over 2. And this would be the sine of pi over 4 is the square root of 2 over 2. And this would be, radians would be applied if we did that. So now what I'd like to do is go back to the unit circle. And with the unit circle, I would like to embed the 45-degree angle here with the triangle. And then this is the point here would be if I go over, here this is square root of 2 over 2. And this here is square root of 2 over 2. So that point there is x is the square root of 2 over 2, and so is y. And this is nice because whenever you have this pair, this is going to get you the cosine of whatever that angle is. See, that's the cosine of theta. And this is going to be the sine of theta. So we actually have set in there, see, in general. We have this in general. Now we have for the 45-degree case done. And then what I do in the book, which you can refer to here, is I simply put one on the other side. And then I was able to get here 45 plus 45 plus 45, which is 135. I was able to get the cosine of 135, which is a negative, say, here. And negative, this square root of 2 over 2, and the sine is still a positive. Isn't that very, very neat? And then we exploit this idea and put 45-degree triangles like everywhere here as we can. And these are all going to be square root of 2 over 2 with either plus or minus signs. And now we have sines and cosines of 45. And we could have the 135, and we can go over to, we can do a lot of it. Actually, the sine, the 90 is an easy case because the sine of 90, if we look at this, as this triangle goes more and more like this, more and more like that, the sine becomes 1, and the cosine is 0. So just imagine this triangle here, really steep like that. Cosine is going to shrink down, and if you have a triangle like this, very, very small, the cosine here is going to approach 1. So the cosine of 0 degrees is 1, and the sine of 0 degrees is 0. And then you can get the 180. You can get all these. So that's, I'm trying to review for you in a short period of time, a lot of trigonometry all at once. And to continue with another favorite triangle, and that is this one here. We want to look at this cool triangle here, which I have in the text, where this side is 2, this side down here is 2, and this side is 2. All the sides are equal. Now, if all the sides are equal, then all the angles are going to be equal. It's a very symmetric figure. So each angle would be, well, we have 180 degrees for the triangle divided by 3. Each one's going to be 60. 60 degrees, this is going to be 60, and this is going to be 60 here. And what I'm doing is dividing the 60 in half so that this is a 30. So I have a 30, 90, 60. So since I divided this in half, then this is going to be 1. I know that because it's 1/2 of 2. I know this is 2 because I set it up that way. I don't know what this is, but I can by the Pythagorean theorem. I take the hypotenuse and I square it to get 4. Minus 1 squared, and that's 3. Take the square root, and I have here the other side. But that means I can now write down the cosines and sines of 30 and 60. The cosine of 30 would be the adjacent, that's this one here, that's root 3 over 2, the hypotenuse. And the sine of 30 is this one here, 1 divided by 2 is 1/2. And then I can get the cosine of 60. Cosine of 60, the adjacent is 1, and I would divide by the hypotenuse 2. And the sine of 60 would be the opposite, square root of 3 divided by 2. Now, once when I have this, now I can have lots of fun, and I could now embed here, here's a 30-degree angle, see? And here's my 60-degree angle. And I can go and play the same game, you know, have 30s and 60s on the other side and down below, and figure out all of the sides and get all the cosines and sines for so many different angles. And here's a master diagram for you where we have 0 degrees, 30 degrees, 45, 60, 90, 120, and I have the corresponding cosines and sines. Remember that each of these, the first one on the left is the cosine of the angle, and the one on the right, let me just go ahead and fix that. The one on the right is the sine of the angle. So these are all cosines and sines, and you know all these from building it up from scratch. All right, and here I have also the radians for you. 90 is pi over 2, pi is 180, and see 3/2 and all that. So you should think about this. Look at this book review and think about this so that you can review your trigonometry. This is a very comprehensive review of the basic ideas. Then what we do is you make these red points and put them on a plot where we have y and x. And when we do this, say for the sine, now here using the t as the variable as we go around here with the various t value, t is the angle, then you get this plot and you get to understand the nice shape of a sine wave like this. Now when I was in high school, I thought this is a very complicated wave, and I thought a straight line or a parabola would be easier to understand, but I was wrong, because if you simply shake your hand up and down in the most natural way like this and go out like this, well, if I do it really naturally, you will get the sine wave. This is a little bit weird. And I often do a demonstration in class where I have a student and push them across the room, where I tell them to just shake the chalk up and down, not think about it, and we push you out. So it's easier if someone's just doing this up and down in a natural way, and then you push them out to the right. One person can't do it easily. Sure, all right. Okay, so you're going to go up and down, all right, and just even look this way. Right, just up and down, up and down. Up and, yeah, you can start doing it now. Right. Up and down. And then now they're going to push. Exactly. Exactly. This is beautiful. All right, stop. This is good. This is good. This is good. This is good. But here's an app that I published with a high school student, where as we shake up and down here, by going around a circle, then the y is shaking up and down. Because see, the y here that goes to 0, then y below and up and down. And when you do that, you then shake off this nice sine wave. So that's a neat app that you can have fun with and play with. And then there is here a nice little table for you to review, which has all the things that we have discovered from our unit circle. And I point out here for you that the cosine has the same values of the sine if you shift it. So what we have done here is take the sine wave and shift it to the left. And by shifting it by 90 degrees, or pi over 2 to the left, then say here is your pi over 2 right there. This is pi over 2. This is pi over 2. And if you shift that to the left, you get the cosine. You get the cosine. And this is where I learned about shifts back in the old days. But I want to show you a neat way to understand shifts. If I have a function, f of x, where I simply note that f of 0 is equal to some peak, and I'll just write down peak, I don't care what the value is, then if I want to know what the function is over here, say this is the g of x function. See, what is g of x? Or here in my notes, it looks like I called it h. All right, so we'll call this h of x. Then I claim that if h of x is equal to the original function, x minus d, this is going to put the peak at d. And they say, well, why do you put a plus sign? Well, now trust me with this. Let's keep the minus sign. Then if I have x being d, then this is f of d minus d, and that is f of 0, and f of 0 is the peak, so that's the one that works. If I put the plus sign, I wouldn't get this result. If I had the plus sign, I would get d plus d, 2d, which would not be, it'd be 0, because this function here goes to 0 everywhere else. That wouldn't work. But by putting x minus d, I shift to the right. So if you want to shift to the right, you put the minus d in. And that's what we're, have a general rule here, that fx minus d shifts to the right, and fx plus d shifts to the left. So here, I want you to think about this and read this on your own. What I have in the book here, think about these shifts. These are very, very important in engineering and mathematical physics to understand. Okay, so after you review that, you'll get to this page, which is a nice page that shows an angle. And then here, this is a pi over 2 minus the angle. These are complementary angles since they add up to pi over 2. That's a definition. And you can see that the sine of theta here, which is the opposite over c, is equal to the cosine of the one up here, because this is the adjacent then over c. So you have this neat little formula. And the cosine is an even function when we have our unit circle like this, and we have, say, an angle theta like this. And then if we go minus theta to come down here, see with the minus theta, the cosines are the same. That's not true with the sine, because see, the sine would be the altitude. Here you go up and here you go down. So it's nice to know that the cosine of theta is equal to the cosine of negative theta, because see, this is a plus theta, has the same run as the negative theta. This is a negative theta, but those are the same. But with the sine of theta, that's up. The sine of negative theta is going to be a y, is going to be down. That's going to be negative. So what we say here is that the cosine is an even function, and the sine is an odd function. Even function means if you change the argument from x to minus x, or from theta to minus theta, you get the same value. And here you get a negative. And that's why for the cosine, it looks the same by a reflection symmetry. And the sine, on the other hand, if you go to the right and go to the left, you have opposite. This is you going up, and here you're going down. Here you go to the right, it's the same on either side. So I want you to think about that also. That's very, very important. Here's a summary of what we have been talking about. First, we talked about shifts, and then we talked about this relationship here. Notice that the sine of theta is equal to the cosine of the quantity pi over 2 minus theta, but because this cosine is an even function, we can flip the order here. In other words, insert a minus sign in front of this whole expression, and that's true. Now, from our shift property, when we have the minus sign, we shift to the right. Now let's look at this here. This is the cosine up here, and if we shift it to the right by pi over 2, it would bring it right to here. This is pi over 2. So this is a visualization of this relationship. So this pulls together the shifting and this identity. Once again, we have the sine function here, the sine of theta, and you can get that by looking at the cosine of theta and shifting it to the right by pi over 2. And remember, when we shift, we put a minus sign after the variable. Theta minus pi over 2 shifts the peak to the right, and in this case it is a peak. And then the last thing I want to do is give you a visualization of the big six. The big six, and I refer, you can look at the notes for this, because this is a lot of review that's going on. It does require you to spend some time with the book to look at these things, to work these things out. All right, this is just giving you a little summary of things found in the book. I have drawn here a triangle, a right triangle, and here I have constructed one that has the same angle coming down and the same angle up here, so that I have similar triangles. So these triangles are similar. To have similar triangles, it just means that you have a scaled up version or a scaled down version. For similar triangles, one way to think of it is that the angles are the same. So this angle here would agree with that angle. This angle here would agree with this angle. The 90-degree angles agree. It's just that this one's bigger than that one. But they're similar, which means that to get this one, if I double this side to get this one, I need to double this side to get that one, and double that one to get that one. See, it's like a scale factor. You can multiply a triangle, all the sides, keep the angles the same by a half or a fourth, and you get a little miniature triangle, the same shape, the same angles, just different lengths. So that's what we did here. We have this triangle, and then we have a similar triangle, because if you have a theta and a 90-degree angle, the other one has to then be determined. So if I have a theta and I have a 90, if I have a theta and I have a 90, I have a theta and a 90, and a theta, now remember that's the z, so their thetas are the same, then all these triangles are similar. Many similar triangles here. So the trick is, with the similar triangles, and I'm going to have you work this out on your own by looking at the book, I show you in detail by similar triangles that when we find A, B, C, and D, guess what we get? This is an amazing result. What we get here is we get the big six. In other words, the cosine and the sine are the first two we started with, but we find that this one here is the cotangent of theta. Yeah, this length here, isn't that wild? And then this one down in here is the tangent of theta. And this big one down in here is the secant of theta. And here, this one here is the cosecant of theta. Now, I refer you to the book to see these derivations. This is very cool to have one diagram that shows you a picture of the cosine of theta here. And here is your sine of theta. And then you see your tangent of theta somewhere, a cotangent somewhere, the cosecant somewhere, and the secant somewhere, all in one diagram. Amazing. So I know this review toward the end did not show detailed steps. I'm requesting that you look at the textbook that I put up at drphys.com, and remember that the text sometimes doesn't get put up exactly when the video is made, because I wait until the chapter is done, everything's done. Now, since this course on calculus is broken up by chapter, as soon as I have this video up, you will have, at the drphys.com, you will have the notes. So toward the end of this discussion, I want you to spend more time on the text, reading the text carefully, and understanding all those concepts toward the end of our discussion. So that's a lot to cover, like in one chapter, one class. I did not cover all trigonometry, but I did cover the basics in some comprehensive way for you to understand before we go into our calculus section, where we will take the slopes, to find the slopes of all these trigonometric functions, cosines and sines, a tangent, cosecant, whatever. And this part of our course, the first part of our course in calculus, is to find slopes of all of our standard functions. All right, so I hope you enjoyed this, and I hope this is getting you psyched up to start calculus very, very soon. In fact, that would be the next chapter.